students, this is Dr. Mohga, and today we're going to be talking about particle model of matter. Let's start with a review of what we covered last session. Solid particles are packed tightly in a regular fixed pattern with very little spaces between them, so they move by vibrating in a fixed position. They have very strong attractive forces between the particles, putting them in a fixed shape and volume, cannot flow and cannot be compressed. Liquid particles are close together, but not in a regular pattern. They have very small gaps between them, so they can slightly be compressed. They slide past each other. The forces are a bit weaker than those of solids, and they have a fixed volume, can flow, and take the shape of the container. Gas particles are randomly arranged and spread far apart. They have large distances between the particles. They move quickly, randomly in all directions with very weak attractive forces, making them move all over. And they have no fixed shape, no fixed volume. They can be compressed because of the spaces between them, and they expand to fill the entire container. So here's a summary of what we just said. For solids, they have strong forces keeping them tightly in place with very close, they are very close as particles. So they have a fixed shape, volume, cannot be compressed, cannot flow. Liquids, they have medium forces, making them slide past each other. They have very little gaps between the particles, making them have a fixed volume but no fixed shape. They can flow, but hard to compress. Gases have very weak forces between the particles, making them move freely. And they are very far apart with lots of space, so they have no fixed shape or volume, can flow easily compressed with fast diffusion. As we're moving from solid to gas, we have to gain kinetic energy and the particle motion increases. And the forces of attraction decrease from solid to gas. Here's an example. Compare particle arrangement and motion in solid and gas. Explain how these differences lead to different properties. I want to talk about two things: particle arrangement and motion. So for solids, they have a regular arrangement, and their motion is vibrate in a fixed position. They said how these differences lead to different properties. Okay, so those two things will make sure that I have strong forces between the particles. I will have a fixed shape and a fixed volume. Gases, particles are their arrangement. They're far apart. They move in random directions. Hence, weak forces, so no fixed shape, no volume, and can be compressed easily. So the stronger forces and close arrangement in solids explain their rigidity, while weaker forces and large separation in gases allow them to expand and flow freely. Another example, explain why a gas can be compressed easily but a solid cannot in terms of particle spacing and forces. As we said, gas particles have a lot of space between them with weak intermolecular forces, so it's easier to push the particles closer together and get them compressed. In solids, particles are already tightly packed with no spaces between them and very strong forces, so they cannot be compressed. Here's an example that I want you to try on your own. Two containers of equal volume are filled with the same number of particles of the same substance, one in a liquid state and one in a gas state, without changing the number of particles. Explain why gas can be compressed but liquid cannot. Pause the video, try it on your own, and then unpause. Compressibility depends on how much empty space, so it's about the volume, not the mass, that exists between the particles. So in a gas, particles are far apart and move freely, leaving large gaps between them, which allows them to be compressed and come closer together. In a liquid, particles are already very close with tiny gaps between them, so it's very hard to compress. So the large interparticle spaces in gas allow compression, while the closely packed particles in a liquid resist it. Now let's move on to temperature and kinetic energy. Temperature is a measure of the average kinetic energy of particles in a substance. And kinetic energy is proportional to the square of speed. That means that when the temperature increases, the particles will move faster, collide more often with greater energy. With temperature decreasing, particles will move slower and collide less often with less energy. Now let's talk about this very famous temperature, which is the SI unit of temperature actually, Kelvin. Kelvin is the temperature at which the particles have no kinetic energy. So basically there is no movement. When they tried to equate Kelvin with degrees Celsius, they said that, first of all, we agreed that Kelvin is known as absolute zero. So Kelvin is known as absolute zero, and it's a temperature. How do we convert degrees Celsius to Kelvin? So 0 Kelvin is equal to minus 273 degrees Celsius. So to convert from Kelvin to Celsius, I will subtract 273. And from Celsius to Kelvin, I will add 273. As I tell my students, alphabetically, C comes first, then K. So from C to K, you have to add, and vice versa. Okay? All right. Let's move on. Here's an example. A container of gas is heated. Explain how this affects particles in terms of motion and kinetic energy. As we said, when temperature increases, particles gain energy, move faster, kinetic energy increases, so they collide more frequently with greater force, increasing the pressure. So as temperature increases, particle speed increases, kinetic energy increases, and of course, pressure increases. Here's an example I want you to try on your own. What happens to the motion of particles as temperature of a gas approaches absolute zero? We said absolute zero is? Yep, Kelvin. So, as temperature decreases, kinetic energy of gas particles decreases, so they move more slowly. At absolute zero, particles have zero kinetic energy and stop moving completely, which is basically at 0 Kelvin. Gas pressure. What happens when I put more pressure on a gas? Gas pressure is caused by collisions of gas particles with the walls of the container. So whenever they give you a question asking you, what caused the increase in pressure? Always remember to talk about the collision with the walls of the container. So each time a particle hits a surface, it exerts a tiny force, which adds up to the total force. So pressure is total force over area. So if I increase the force, I increase the pressure. If I increase the area, I decrease the pressure because they're inversely proportional. Okay? So in a gas, particles move randomly at high speeds. They collide with the walls of the container frequently and with force. Each collision transfers momentum to the wall, creating pressure. The more frequent and forceful the collisions are, the higher the pressure. So what are the factors affecting gas pressure? Number one, temperature. Increasing temperature makes them have more kinetic energy, move faster, more collisions with the walls, so more pressure. Volume. If I decrease the volume is relevant to area a bit, so we said they're inversely proportional. So if I decrease the volume, I have less space for particles to move, so particles will hit the wall more often and pressure increases. If I have more number of particles, that means there will be more collision, more force on the walls, pressure increases. Here's an example. A student uses a pump to inflate a bicycle tire. As the air is pumped in, volume inside the tire remains nearly constant, but the number of gas particles increase. Why the pressure inside the tire increases using the particle model? Because adding more particles will result in more collisions, which, due to pressure equal force over area, will result in more pressure. Okay, so in gases, the force created by particles colliding with the wall of the container causes the collision to transfer momentum to the wall and give a tiny force. Millions of these collisions per second give an actual measurable pressure. Okay, so basically this is here or there the same thing. So what causes changes in pressure? We said already temperature and we said volume. I just wanted to break it down to you in points. Particles moving faster with temperature, so collide with wall more frequently and with greater force. Here I put 2 points. Third point, total force on wall increases. And fourth point, I prefer you always write the equation. Pressure is force over area, so pressure increases. If I decrease the volume, first point, particles will have less space to move, so they will collide with walls more often, more force per unit area, and since pressure is force over area, the pressure will increase. Here's another example. A sealed rigid container of gas is heated. I explain in terms of particle collisions and force why the gas pressure increases. Like we said, when there is a faster collision, there is greater force, and since pressure is force over area, there will be higher pressure. Try this one on your own. Gas particles exert a total force of 600 Newton. That's my force. On the inside surface of the container. The total area is 0.75 meters squared. That's my area. Calculate the pressure and give your answer in Pascal. All right, so pressure is force over area, 600 over 0.75, and Pascal is basically Newton per meter squared. So my units are correct. That means I can easily write Pascal without any further conversions. Now let's talk about Brownian motion. This is one of the most common questions that comes in this lesson. Brownian motion is a random movement of tiny visible particles suspended in a liquid, which is a gas, a liquid or a gas, basically any fluid. Here, Brownian motion, to cut it short, is first of all observed under a microscope. Second of all, it's a zigzag movement due to the collision of a particle with a gas or a liquid. So this zigzag motion is caused by collisions with smaller, so my particles are colliding with smaller, invisible, I cannot see them, particles in a fluid. These are the atoms or molecules of the gas or the liquid, which I cannot see, the invisible ones. They're very small, they're light, and they move quickly. So if I'm talking about a specific particle, I can see the red particle. It's colliding with some other particle in a fluid, which I cannot see under the microscope. It's invisible. But what I can see about my red particle is it's moving in random motion. So what is Brownian motion? It's the movement of the particle in random zigzag motions due to the collision with smaller, invisible particles in the fluid. This experiment was done with two things. It was done smoke with air. I can see the smoke, but I cannot see the air. So my smoke particle is bombarding with the air, causing a zigzag motion due to the collision with smaller, invisible air particles. And they've also done it with pollen and water. Same scenario. The pollen particles are colliding with the smaller, invisible water particles, causing a zigzag motion. Okay? So this provides evidence that there are atoms and molecules that are invisible, but they result in other particles moving randomly due to the collisions between them. Here's an example of Brownian motion. When viewed under a microscope, smoke particles in still air are seen to move in continuous random jerky motion. Explain the observation using kinetic particle model. Smoke are microscopic particles, so we can see them under a microscope. The air around the smoke particles is invisible, fast-moving gas molecules. So the light, fast-moving air molecules collide randomly and unevenly with the smoke particles. Who's colliding with whom? The smaller particles are colliding with the larger particles, causing random motion, zigzag motion, which supports the kinetic particle model, saying that particles of a gas are constantly moving and colliding. Another example, when viewed under a microscope, pollen grains suspended in water are seen to move in a random jerky motion. Explain this observation. Same thing. We're going to say that the pollen, which is the bigger particles, are being collided by the water, which is invisible, causing the random motion. So the pollen, which is a microscopic particle, is surrounded by water, which are invisible molecules in constant motion, bombarding with the pollen and causing random and unbalanced motion, or continuous random zigzag motion, known as Brownian motion. That's all for today. Please let me know if you have any questions. Have a beautiful day.